What is up, amigos? Today we're talking about what is viscosity. We'll be going through what it is, how to calculate it, and something called superfluids. So first of all, what is viscosity? Well, let's say we have a fluid moving along here, and we have it like that. And let's say this part here is moving along at 1 meter per second. Then this part here is moving along at 2 meters per second, and this one was at 3 meters per second. So between this one and this one, we have a difference of 1 meter per second, and similarly here. So the interaction between this layer that's moving at 1 meter per second compared to this layer means that there's a relative motion between them. And viscosity is effectively just the damping of this motion to try to stop it from these two layers shearing across each other, so they'll just move at more at one block as opposed to two different layers. And the greater the viscosity, the more resistance there is to this relative motion between the different parts of the fluid. So, it's, for example, water that has quite a high viscosity compared to air, but then honey has a higher viscosity compared to water. So it's actually quite easy to calculate viscosity. And to do that, we look at, let's say, this example here. We have, at one point in time, this particle of fluid on the ground. And this is at time t1. Now we apply a force here, the shear force, at this top part here. Now, a little bit of time later, at time t2, so delta t is the difference between these two times, we have the block again on this surface, but now instead of being this rectangular shape, it's now more of a trapezoid shape. And the reason why is because we've applied this force at the top part, but not anywhere else on this block. So this top part has now moved along, and as we go down along the block, there's relative motion between the top layer and the second top layer, which means that the second top layer will also move a little bit along, but not as much as the top layer because of that viscosity trying to hold it back, as well as then the second layer compared to the third layer, there's that viscosity again, so it sort of dampens out a little bit more and more until we get down to the boundary. And now there's no relative motion between the layer directly touching the boundary. That's called a no-slip condition. So the top layer has moved the most. And if we were to draw the original box, so we draw this sort of ghost shape here, the distance that this has moved in time delta t is x1, let's say. Now, let's go down to the second layer, the second top layer, and look at how much that has moved in the same time, which will then be x2. So if we were to look at the shear stress, so shear stress just tells us how much stress there is when we have fluids moving over each other or fluid moving over a surface, just this relative motion. We use the letter tau, the Greek letter tau, and this is proportional to how much the velocity has changed based on how the distance between these two layers. So let me explain what's going on here. If we calculate the velocity of this top layer, we know the distance that it has moved in the amount of time it has moved. So u1, which is the velocity of this top layer in this time that we've been looking at, is actually just x1 divided by delta t. That's very simple. And u2, which is the velocity of the second top layer, is now x2 divided by delta t. So tau is the difference between these two velocities, u1 minus u2, divided by the distance between them. So we have going from the base to the top, that's y, but then going from the top to the second layer is now y, let's say delta y. So now this is delta y here. And this is what the shear stress is proportional to. And if we were to put this into the derivative form, we would then just say du on dy. So that's the continuous form of it. Now, if we were to, we don't know what the viscosity is yet, but we can calculate this quite easily. So if we were to draw a graph of the shear stress on the y-axis and the du on dy, the change in velocity as we go up or down this distance, we will then potentially see like what it is. We'll see if it's linear or not linear. We'll cover the linear case first because this is called a Newtonian fluid first, and this is the most common one that we use in aerodynamics at least, and most of fluid mechanics. So let's say this line is linear, this relationship between the two is linear, so it's proportional. That means that if we were to calculate the slope of this line, we'll actually find that it's something called mu, which is actually the dynamic viscosity. Dynamic. We often don't put dynamic in, but that's what it is technically called. So what this means is if we know the dynamic viscosity from this line, we know the relationship between them, we can now say tau equals mu, the dynamic viscosity, times du on dy. So we can just rearrange this equation to find mu equals tau divided by du on dy. So if we know what the shear stress is, and we know how much the velocity is changing with distance, we can find the dynamic viscosity quite easily. So that's how we calculate it. And we also can calculate the kinematic viscosity as nu, which is mu divided by the density of the fluid, rho. So that is how we calculate the dynamic viscosity and the kinematic viscosity. Now let's talk about one final thing, which is called superfluids. And the reason I want to talk about this is because it is very cool. And we've kind of known about it for about 100 years or so, but it wasn't really acknowledged until about 30 years ago or so. And what happens is if we have a superfluid, this is a fluid that has no viscosity. So mu and nu both equal 0 in this parcel of fluid. That means that if you apply shear stress anywhere along here, there is no viscosity. This layer that it's been applied to will just freely move along, and it will dissociate completely from the rest of this fluid parcel. And superfluids are quite uncommon as far as we know. There are really only two main superfluids that we know of. One is helium-3 and one is helium-4. So helium-3 is the common helium that we are used to. Helium-4 is a common isotope of helium-3. And these heliums will only become a superfluid under a certain condition, and that is if helium-4 is less than 2 Kelvin in temperature and helium-3 is less than 2 millikelvin in temperature. So in other words, it has to be super cold to then elicit this superfluid property of having no viscosity. Now, one final thing I should mention is, what if this line wasn't linear? I forgot to mention this earlier. So let's say if the line goes like this or goes like this. This means that the fluid is no longer Newtonian, it is called non-Newtonian. And one very common example of this, which we have seen in the last 10 years as an internet fad trend, is something called oobleck, which is cornstarch and water, and sometimes food coloring or whatever to make it look cool. But oobleck and other non-Newtonian fluids result in having viscosities that change with different shears and different forces applied to them. So the viscosity is not constant. So what this means is, for example, oobleck, if you were to punch it, as we've seen, or hit it really hard very quickly, because you're applying so much force very quickly, the viscosity skyrockets and then creates this solid effectively instantaneously until the force has dissipated, and then it can just go back to being runny and having a fairly low viscosity. So that is what a non-Newtonian fluid is, and that is what viscosity is, how to calculate it, and superfluids. So if you like this video, make sure to like and click the subscribe button, and I'll see you. Peace amigos.